Every time we have had two polynomials being multiplied, the way we found the derivative was by using distributive property, expanding and simplifying these functions, and then using our basic power rule. But that's obviously tedious, and sometimes it's just not the most efficient way to do things because there's too many terms or the exponents are too high. So we need to add on our product rule. And our product rule is going to allow us to more efficiently find the derivative of something of the form f of x times g of x. And we're going to start off with a little proof. And the little proof is going to involve first principles. Now, first principles used limits. It was the limit as h approaches 0 of f at x plus h minus f at x all over h. But we're going to do this for our combo function, our product function of f at x times g of x. So let's start. So p prime of x is equal to the limit as h approaches 0 of f at x plus h times g of x plus h, so that's like our y2, minus f at x times g of x, so that's our y1, all over, it would be x plus h subtract x, so x2 minus x1, but the x's cancel out. There it is. There's our first principles applied to this product function. And at this point, it kind of looks like I have nothing I can really do. So I'm going to do something I do with completing the square, which is adding and subtracting the same term so it could get me somewhere. And the term I'm going to add and subtract is going to be f at x times g of x plus h, a little combo of the things I see on my page here. And I'm going to add and subtract it. So I'm going to subtract it first. Then I'm going to add it. And that way I'm not actually doing anything, but it is going to allow me to get some factoring in here. And now I'm going to pair these up. I'm going to look at the first two terms, and they both have g of x plus h in common, so I'm going to factor that out. I'm going to look at the second two. They both have an f at x in common, so I'm going to factor that out. And why this is nice is because right here, that just looks like a generic first principles. Oops, sorry. Should keep it a single fraction here. I'm getting ahead of myself. And in the second pair, I'm going to factor out an f at x. So that I'm left with g of x plus h minus g of x. And here as well, it looks like a nice first principles. Now, that's great and everything. I see my first principles. Now I'm going to use my limits properties, which states if I have a function that has addition of multiple functions or multiplication of multiple functions, I can kind of distribute, if you will, that limit in. So I'm going to break this down into multiple limits. When two functions are attached by multiplication like they are here, they can be broken down. If they're attached by addition, I'm going to break them down. So first thing I'm going to do, I'm going to split these in half. And just to save some space here, I'm just going to use my eraser and write plus the limit of h over 0. And there, I split off my two fractions, okay? Boom. Now I'm going to split up the fact that these are attached by multiplication into two more limits. So I'm going to have the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of f at x plus h minus f at x all over h plus the limit as h approaches 0 of f at x times the limit as h approaches 0 of g of x plus h minus g of x all over h. This is first principles, this is first principles. Those just represent the derivatives of those specific functions. So when I evaluate h approaching 0 into g of x plus h, I'm just going to replace h with 0, and I'm left with g of x. The next part is the first principles, so it's the first derivative of f at x, plus there is no h for me to sub in for f at x here, so that'll just stay as f at x. And then the other limit is again first principles, so the first derivative of g prime. And look at what we have here. It looks like we're just taking turns taking the derivative of one of our functions. The first time we take the derivative of f prime and multiply it by the original g of x, and in the second one we take the derivative of g of x and multiply it by the original f at x. And that's exactly what our product rule states. And if I have multiple things being multiplied, not just two, if I have three, like in this function here, again, I'm just taking turns. In the first part, I copy everything except f at x, it's the derivative. In the second part, copy everything, but g of x is the derivative. The last part, copy everything, but h of x has its derivative. So let's try applying this product rule. For a, f prime of x, earlier, we would have expanded and simplified this and used our power rule, but now I'm going to take turns. So first, I'm going to take the derivative of my first bracket. The derivative of 2x minus 1 is just 2. And then I'm going to copy paste the second bracket. Plus, now I'm going to take the derivative of the second bracket. 2x plus 3 is the derivative of x squared plus 3x. And then copy paste the first one. Okay, and it doesn't matter what order you put these in. Like if you wanted to write f at x first and then the derivative after, that's no problem at all. And then from here, actually I said keep an unsimplified form, so we're just going to stop here. We're just practicing the rule. But if I had to do more with this derivative, maybe set the derivative equal to 0 or set it equal to a specific slope, then I would expand and simplify this, clean it up. But in this case, we're just practicing the rule itself. So for b, g prime of x, I'm going to take the derivative of my first function, and that's going to be 6x, that's it. Copy paste the second one, plus, now I'm going to take the derivative of the second function, 2x minus 1, and I'm going to copy paste the first one. Done. If I have three terms, I'm just taking turns, taking the derivative of each function. So I'm going to start with the derivative of the first bracket, x plus 1, the derivative is just 1. Copy paste everything else. Plus, I'm going to take the derivative of the second function. That's 2x plus 3. Copy paste the other two. Plus, I'm going to take the derivative of the last function, just 1. Copy paste the first two. And there we are, the derivative of this function. Instead of me using distributive property and then using power rules, I could have done this. Now let's see the power of a function rule. And this is if I have a function to the power of an exponent. So it's like having x to the power of an exponent, but I actually have a function inside. And it's actually getting us ready for something called the chain rule. But this one is going to be more specific to polynomial functions or just functions where you just have variables to the power of a certain exponent. So it could, you could have a square root, or you could have it be a negative exponent, so it's rational. But this is kind of getting us ready for chain rule, where we could have other types of functions like exponential or sinusoidal once we actually know how to find those derivatives. But for now, this is the power of a function rule. So what you're going to do is start off by taking that exponent on top of your bracket, bringing it down, and then subtracting 1 from the exponent, just like with the power rule. And you'll notice that the original inside function stays the exact same. So at first, you're just taking the derivative of the exponent part. Then at the end, then you take the derivative of what was going on inside. So for this first example, g prime, I'm going to start off with taking the derivative of something to the power of -2. So I'm going to bring the -2 down. I'm going to copy paste whatever's going on inside. I don't care about that just yet. I'm going to subtract 1 from the exponent. And now I remember, oh, there was an inside function. Let me take the derivative of it. 9x squared minus 10x plus 2. Okay. Now for this one, I did say I want restrictions if we need them. So I am going to clean this up. I'm going to start off by bringing this part down to the denominator. So the -2 stays on top. The 9x squared minus 10x plus 2 stays on top. And then while I'm bringing this down into the denominator, I'm also just going to factor out an x. And that's all to the power of 3. And now because I want those restrictions, I'm going to factor the denominator further, that trinomial, and then I can state my restrictions. I don't care about factoring the numerator because I'm not looking for the zeros, even if it is factorable or not. Okay. If we want, we could also distribute that exponent of 3, so it's just x cubed, and then each bracket will be to the power of 3. We could do that as well, but it doesn't matter. So when I factor the denominator, I'll just do a crisscross, and I can show it on the side. I just don't feel like it right now. And here we are. So that our restrictions are that x cannot equal 2 over 3 or 1. There we are. Next. Here we have a little combo question. It's a product rule because I have two functions being multiplied. So function 1 and then function 2. But it's also this power of a function rule because I have this exponent up at the top. So we have to be very careful when we take the derivative. We're going to start off by taking the derivative of the first function. So I'm going to bring the 3 down. I'm going to copy paste the bracket. I'm going to go to the power of 2. I'm not done with the derivative because I still have to take the derivative of that inside bracket. I have now taken the derivative of that first function. Now I can copy paste the other one. Plus, now I'm going to take the derivative of that second function. This one will be much quicker, 4x minus 4. And now copy paste that first function. Now this is not going to have a restriction, but I do want to clean this up a little bit. Now when I see this, your first instinct might be, oh gosh, I have to expand and simplify this, but we are not going to do that. This is a unit, this is a unit, and each of them have this 5x minus 4 bracket in common. The first unit has it twice, the second one has it 3 times. So I'm going to factor out like a GCF, 5x minus 4 to the power of 2. And when I do that, the first unit still has the 3 and the 5, so I'm just going to write 15 times the 2x squared minus 4x plus 6. And the second one has the 4x minus 4, and it still has one more bracket left. And now this I can clean up. This is much quicker to expand and simplify. And this is a good strategy to use, especially if I had to set my derivative equal to 0, because if I expanded and simplified from the top, I'd be left with a quartic function, which means you would then have to go and factor that, which would be a lot more tedious than us doing this GCF factoring here to make our lives already pre-factored and make it a little easier. So now 30x squared minus 60x plus 90 plus 20x squared this is a 4, so minus 16 and minus 20, so minus 36x plus 16. And then I'll just finish collecting my like terms. 50x squared minus 96x plus 106. And there we are. All right, let's go to our final one before 2 little word problems. So this is a rational function, and we will find and we will learn the quotient rule later on. But for now, using the skills that we have, I'm going to turn this into 2 things being multiplied. The numerator times the denominator to the power of -1. They mean the same thing. And once I've done this, now it's just like the previous question. I have a product rule. That's my first function. That's my second function. But I have a chain rule, or sorry, a power of a function rule as well. So p prime of x is going to be the derivative of the first function. There it is. Copy paste the second. Plus time to take the derivative of the second function. So I'm going to have to bring that -1 down. So I'm actually going to turn that plus into a minus. Okay. So -1, write the inside. Now it's to the power of 2. Now take the derivative of the inside. And now write the original first function. Okay, time to clean this up. I see negative exponents, so fractions are coming in first. The numerator will have the 1 times 2 is 2, times the 3x plus 2, and 2x minus 6 to the power of 2 will be in the denominator. I would like to unify these fractions, so I'm going to multiply top and bottom by 1 more 2x minus 6 bracket, so that we have 6x minus 18 for the first fraction. And here I'm distributing the -2 in, so minus 6x minus 4. And then just collect your like terms. The 6x's cancel out, and we're left with -22 over 2x minus 6 all to the power of 2. And x cannot equal 3, because that's what would make the denominator 0. Now, I could actually take this a step further if I wanted to. I could factor out a 2 from here, which would be raised to the power of 2, and then reduce the -22 with the 4 that would be there. But this is fine as well. All right. So we've gotten our product rule. We've done the power of a function rule. We can deal with rational functions now by bringing the denominator and making it a negative exponent. So that's fantastic. We've expanded on our rules. Now let's do typical questions we've seen in the past that involve these new rules. So we're going to start off with a displacement function. So the position s in centimeters of an object moving in a straight line is given by s at t equals t times 6 minus 3t to the power of 4, where t is greater than or equal to 0, and where t is the time in seconds. Determine when the object is slowing down and speeding up. So for these types of questions, slowing down, speeding up, I need to figure out when velocity is equal to 0, when acceleration is equal to 0, and then see when the signs are positive. So I'm going to do a sign analysis. Remember, velocity is the first derivative of displacement, acceleration is the second derivative of displacement. And now, let's start off with our derivatives. And I have 2 functions. Function 1 is t, function 2 is the bracket to the power of 4. So, the first derivative, or velocity, is equal to the derivative of t is 1, I'm not going to write it, times the original second function, plus the derivative of the second function, bring the 4 down, write the insides, it's now to the power of 3. Now let's take the derivative of the inside, which is just going to be -3, and then write the t. I am going to clean this up a little bit. I don't want to expand and simplify this, so I'm just going to factor out the common bracket, which is 6 minus 3t, and it's common 3 times. So when I take it out from this first unit, I still have one of them left over. When I take it out from here, I'm just left with the 4 and the negative 3t, so that's just negative 12t. And clean it up, and we're left with 6 subtract 15t. Okay, perfect. If I set this equal to 0, what are my t's? In this bracket, t is equal to 2, and in this bracket, it is equal to, bring the 6 over, divide out the negative 15, so 6 over 15, reduce it, 2 over 5. So I'll keep these values in mind for my sign analysis. Now let's get that second derivative, which is our acceleration. And again, I have a product rule here. So take the derivative of the first function, bring the 3 down, write the inside, it's now to the power of 2, times the derivative of the inside, which is negative 3. Now multiply it by the second function. This time the second function is a little more complicated. Plus, take the derivative of the second function. The derivative is just negative 15, so I'm just going to write minus 15. And then write the first function. Okay, clean up time. Again, I'm going to factor out. I know I'm going to have to set this equal to 0 and solve for t, so I definitely don't want to expand this out. That would create a lot more work for me. And these units just have the 6 minus 3t in common twice. So when I factor it out from the first unit, this is gone, and we're just left with 3 times negative 3, which is negative 9 times 6 minus 15t. And for the next one, we're left with the negative 15 and 1 remaining bracket. Just going to clean up that second bracket so that we could actually solve. Okay, just gonna do it on the side or right on top just to have a little bit more space underneath. Negative 9 times 6, negative 54, plus negative 9 times 15, 135t. Here, negative 15 times 6 is negative 90. Negative 15 times negative 3 is positive 45t. All right, collect those like terms. And we have, oops, that was supposed to be a 135. 135 plus 45 is 180t. Negative 54 minus 90 is negative 144. And now I'm going to set that equal to 0. And we have t equals 2 again. And t equals 144 over 180, which is going to reduce to 4 over 5. And now I'm going to do my sign analysis using all of those zeros and the velocity and acceleration equations. So velocity, acceleration, and we're going to go from 0 to 2 over 5, from 2 over 5 to 4 over 5, from 4 over 5 to 2, and from 2 to infinity. All right, so you're going to pick test values within each interval. So between 0 and 2 over 5, maybe we pick 0.1 or something like that. And when I plug it into velocity, I end up with positive, negative for acceleration. Feel free to pause the video here and do your test values. I'm just going to go through them a little quicker. For the next interval, I might pick 0.6, negative, positive. For the next one, maybe I pick 1, negative, positive. And for the last one, maybe I pick 3, and they're both positive. So the only place that we are speeding up is right over here. So speeding up when t is greater than 2, slowing down, we have all 3 of those intervals from 0 to 2 over 5, from 2 over 5 to 4 over 5, and from 4 over 5 to 2. And there we have it. Same question, but fancier function. And final one, determine the values of x where the tangent line to the graph f at x equals the square root of 4x squared minus 8x has a slope of 2. So we need the derivative and we need to set it equal to 2. Now, as a reminder, this is the same thing as 4x squared minus 8x to the power of a half. So we can use our power of a function rule. So I'm going to bring the 1/2 down, copy paste the insides, and it's now to the power of negative a half. Now I'll take the derivative of the inside, which is 8x minus 8. Because I do have to set my derivative equal to something, I am just going to clean this up to make my life easier. So the numerator will have 8x minus 8. The denominator will have 2 times 4x squared minus 8x. I could factor out a 2 from here. So write 2 times 4x minus 4. That way we can cancel out a 2. And now I'm going to take this derivative and set it equal to 2 because that's what the slope of the tangent is supposed to be. And now it just becomes a solving question. So I'm just going to multiply 2 by the root and 4x minus 4 times 1. Let's raise all of this to the power of 2 so we could get rid of that radical. So we'll have 2 squared is 4. The square root squared is now just the insides. And here I'll expand and simplify. So 16x squared minus 16x minus 16x, so minus 32x plus 16. I'll distribute the 4 in here. And look at what happens here. The 16x's, if I brought them over, would cancel out. So would the negative 32x's. And then I'm left with 0 equals 16, which no, it does not. And this just means that there is no tangent line that will have a slope of 0. So therefore, no tangent line will have a slope of 2. And there we are. So questions that we've done in the past, but now the functions can be more interesting because we've expanded on our derivative rules.